Yeah, so the problem is you can also hear us now.
Hi, Armando.
Hi. Hi, Roger.
How are you doing?
Doing well. Looking forward to a great Thesis defense.
What kind of cactus is it in the distance? It makes me miss home. I'm from Tucson.
Oh, yeah. Actually, it's probably similar. I don't actually remember if it's kind of it. I was at a botanical garden in Mexico.
Awesome. So just I'm gonna test. Oh, sorry. Go ahead. Great. So Kevin's got his. Can people see? Can people see Kevin's screen share? Great. I'm also going to test as we're getting ready to get going. I'm going to test one other thing, which is I'm going to see what happens when I spotlight Kevin's video. So I think that's supposed to. Did that have any effect on anybody?
Nope.
It looks like he popped up into the top of my screen, but where he wasn't before.
Yeah.
He's still small in the background. Yeah. Or I mean, it sort of depends what view you use. Yeah.
Right. Okay. I think that's a desirable thing to have him spotlighted. I'm not sure, but I'm just gonna.
Yeah. Absolutely.
Yeah.
But
I'm just gonna
talking. He should be.
Yeah, it's probably gonna be fine, but just in case. Yeah. Oh, it wouldn't. Okay. Thanks, Kevin. Kevin gave me clarification. We got some more people coming in.
Also,
and let's see. Oh, go ahead.
Also, on my screen, there's a slider. You can change the relative size of the slides versus the picture of Kevin.
I'm just telling you what I'm doing.
Can we mute people?
Yeah. So, is there a global mute? I thought there was like I did a mute people on entry, but I can't.
You're the host, right?
Is there? Can anybody give me guidance on? I thought I had this setting, but it's set up that I don't think it's working. Is there a way of?
Maybe it's under participants. Could it be under the participants?
Oh yeah. I think you're right.
Oh my god.
Oh,
MIT Tech, guys.
And then Roger, when it's done, can you globally
there? Sorry. Yeah. Go
sorry.
Ahead.
Yeah. I was just gonna say, let's globally mute people unless they like raise their hand during the talk. And there's some like crucial question, but for the most part, let's globally mute people. And then at the end, let's globally unmute so everyone can clap, and then we can do questions one at a time.
Sounds good.
And somebody asked about recording. Let's record. I assume that's okay, Kevin. I mean, you can do what you want with the recording afterwards, but we can edit it or But
so what we're doing, actually, I chatted with Kevin about this. Kevin has somebody else independently recording via Twitch, and so. Number one, everybody should be aware that this is recorded. But I think that's probably okay. Does that seem like it's going to be adequate for our purposes? Sounds like. I think.
As long as it's being recorded, do you mind if we just record it also for Zoom?
I'm fine with it. Kevin, is that okay with you? Okay, good. I'll do that as we actually get started. There's still a few more people coming in, but we are at 1:05, and we have all members of the committee. Is that right? Okay, good. All right, so we're going to get started. So here's the welcome to Kevin Ellis's PhD defense. Thank you for coming. Actually, you know what? I'll even record this part. Okay, recording is starting. We're starting now. Welcome to Kevin Ellis's thesis defense, everybody. I'm Roger Levy, the chair of the committee, and we are about to start. Yeah, I need to unmute Kevin. Okay, I've unmuted Kevin. Let me just briefly say what the parameters are of what we're going to do here. So this is the format of the thesis defense is that the first thing that will happen after I finish this introduction is that I'll turn it over to the committee chair to make a few introductory remarks, introducing Kevin, the advisor, introducing Kevin. Then Kevin will give his talk. The intention is that the talk is not going to, the talk is largely intended to be an uninterrupted process. So please don't, you can raise your hand, but please only do it if you have really crucial clarification questions. The chat is also available, so you can put things in the chat, and there may be opportunities for addressing them in a way that doesn't interrupt the flow of the talk. After Kevin finishes speaking, there will be opportunity for open Q&A by all members of the audience here, and then we'll go into a closed session involving only Kevin and the committee. And then after that closed session, Kevin will leave the session, and then the committee will discuss. We bring Kevin back in, we have a final discussion, and then there's a final public announcement of the disposition. Any questions before we start? Armando, you have a question. Let me unmute you. Go ahead. Armando, are you able to unmute yourself?
There we go. I am unmuted. No, since I'm going to also do part of the introduction, I want to make sure that I get unmuted.
Oh, okay, good. Yeah. All right, great. Okay, so, all right, I'm going to turn it over to the advisor team.
So, Josh, you want to go first? Or if not, I can go first.
Sorry, no. Okay, sorry. I was muted.
Sorry, my fault. My fault.
All right.
You can go first, Armando.
Go first.
Either way, so it's good.
All right. Well, so yeah, it's really my pleasure to introduce Kevin. I think he's been doing really groundbreaking work in this intersection between program synthesis and ideas from program languages and AI, and really pushing the envelope in terms of what people think of as possible to do with this kind of techniques. And I think you'll get a sense of that from the talk today. But I think on top of that, it's been just real pleasure working with him over these years, and I think you'll get a sense of that in this talk as well. Yeah.
Yeah. So I may go on just a little bit longer because I've known Kevin for a rather long time, and I am grateful for this opportunity to just say a few words. Kevin was an undergrad at MIT, so I've known him since he was an undergrad, and it's just been wonderful to watch him grow up here. One of Kevin's qualities certainly was the first thing I noticed about him was that he didn't say very much. He was an undergrad in my class. I think maybe, Kevin, was it your sophomore year when you took my class? Or junior year? Junior year, okay. But I don't remember him saying really anything during class. I first met him when I read his paper, his final project, which was very much a look forward into what he wound up doing for his PhD. He basically developed an approach to symbolic program learning, and it was an incredibly impressive project. It was one of the most impressive projects that I had ever seen for a class project by an undergrad in a class that was taken often by graduate students. And I didn't really even know this person. I was like, who is this guy? And I have to meet him right away. So I wrote to him, and he got involved in research in our lab shortly thereafter, but I didn't work that closely with him. He worked mostly with an advanced grad student in our lab, Eyal Dector. But I already got to meet him. He joined lab retreats, lab sports events. We went up to dinner once or twice, and I knew him enough to know that it would be great if he decided to stay for grad school, and I was looking forward to both working with him more myself and also encourage him to explore connections like to the world that Armando represents and Armando's group, which was a key part of what he did in grad school. And it's been great to co-mentor Kevin with Armando and see him be part of both of these groups. And in that time, through his PhD, he's grown in so many ways. I mean, he was brilliant already, but he really found his individual voice, his research, and he really grew into a leader in so many different ways. You know, he's as those of you who know him will see, and I'm sure this will come through in his talk, he's an incredibly warm person, and he built teams. People just naturally gravitated to work with him, and he wanted to work with others. And he built some great teams that were partly responsible for the research that he's going to tell you about, and just did so much to make our group, and I'm sure Armando's group and every group that he was part of, just better. And that was better personally and better for the research. Really, it's, you know, I think he's grown into all the sorts of things that we who are professors think of as the ideal professor, which is why it's not a surprise that even just coming straight out of grad school, he already got several top faculty offers, and he's going to be joining as a faculty member Cornell in the Department of Computer Science after a gap year. And you know, it's not that many PhD students who can go straight into such a faculty position, but it's not at all a surprise that that's what Kevin is doing, because he's just like a consummate intellectual and personal leader that you would look for. Just one thing about his research, expanding on what Armando said, you know, Kevin's work bridges multiple areas of computer science, both machine learning and program synthesis and programming languages, as well as kind of cognitive science and AI. And I think what he's done here is to, you know, is to really advance all of these fields. He has built what I think of as some of the leading approaches to what I think of as a new kind of machine, or let's say the future of machine learning, that addresses some of the challenges in today's paradigms, like of deep learning, which he'll tell you about, while also building on their strengths. And he's also done things which I think will be influential in the next wave of cognitive science accounts of learning. He's done this by integrating a range of different techniques, which I'll tell you about, and that I truly believe there are very few people in the world, and maybe even nobody in the world, who has the range of skills and the vision of how to combine them that Kevin has had that allowed him to do this work, which I really don't know anybody else who could have done. So that's incredibly impressive. And I would just say, lastly, from a personal point of view, you know, I got into the field to work on learning. My own PhD thesis was on learning. A lot of my group's early work was on learning. But in our group, we stopped working on learning about 10 years ago because it was just too hard. Like we felt like we got to the limits of what we could do with the probabilistic models toolkit that we had. Neural networks didn't seem like they were enough. We knew that something in the space combining those with symbolic approaches would be right. But you know, the learning has always been my passion, and many people think of our group in that way as like studying how humans learn. We weren't really able to make fundamental progress there. But with Kevin, I've been re-inspired to see that that's possible, and you know, that means a lot to me personally. You know, I'm really, it makes me so happy to say now we're back in it. We're actually working on learning, because the things that we always thought could be done, Kevin has showed us how to do. So I've learned an incredible amount from him personally, and I think all of us have, you know, are just at the beginning of learning well how we should really be approaching learning. So on that note, I will stop speaking and let Kevin tell us just a little bit of what he's learned.
Thank you so much for those incredibly kind introductions. I'll try to follow them. And also thanks for coming out over Zoom. I know this is kind of weird, but I really appreciate that. You know, you're all here. So I'll just start right now by saying that you know, I gave this talk the title of Algorithms for Learning to Induce Programs, and I think that's an appropriate title, but a sort of less mechanistic title, which is more about like the goal is something more like building machines that discover generalizable, interpretable knowledge. And so really you should keep both these things in mind, and I'll sort of enter with that. So I want to point out that human intelligence allows us to solve really a kind of endless range of problems. And these go all the way from like cooking to calculus to graphic design. And on a personal level, like what I find so amazing is not just that we can do all this stuff, but the fact that we usually don't need enormous amounts of experience in order to master any one new individual skill. So some things like getting really good at checkers might take a while, but other things like learning to use a new device, like the pasta maker that I put on this slide, you can pick up after just a few minutes of experience. I think that one of the key, really long-term goals of AI is to build machines which can similarly master this kind of unbounded span of problems, while at the same time not needing enormous amounts of experience to learn any one new thing. So, what kind of machine could actually learn all of this? So each wave of AI has made important contributions toward answering some version of that question. The first waves of AI were dominated by what's sometimes called symbolic approaches, and these approaches were actually really successful. They're maybe not quite as trendy today, but they really give us a lot of modern computer science. They give us computer algebra systems like Mathematica, they give us chess-playing robots, and so on. At the same time, these systems were notoriously brittle. They typically did not deal with the messy uncertainty of the real world, and they didn't have a very good story for how learning could work. What's sometimes called probabilistic or statistical approaches to AI addressed many of these shortcomings, and they really give us the first practical and scalable approaches to machine learning. They were used, for example, by the UN to monitor nuclear tests, and they gave us Google up till about a decade ago. Neural network approaches have been tremendously successful, particularly for pattern recognition and perception. And in some sense, they actually do seem to be meeting the challenge that I posed earlier of mastering a wide range of tasks. Like different kinds of neural nets can learn to recognize objects and images or play challenging board games. At the same time, what and how they learn, I think, is very different from a human. They tend to generalize more weakly from their experience. Intuitively, they kind of interpolate rather than extrapolate. And the kind of knowledge they get from that experience is not really formatted in a way that humans can understand. So what I'm going to be talking about today is an approach to artificial intelligence called program induction. And the idea is that we represent knowledge as code, as programs, and we learn by adding to that body of knowledge, by synthesizing new code. You shouldn't see program induction as being in opposition to any of these other AI traditions. Instead, you should see it as trying to take the best from all of them. So why would you want to do this? Why would you want to make machines that learn by synthesizing code? So there's a few reasons. One is that programs tend to generalize very strongly. Intuitively, they extrapolate rather than interpolate. And because of this, you can often learn them from very small amounts of data. Not all programs are human understandable, but they tend to be one of the more interpretable representations of knowledge. They really are the language in which humans design much of the digital world. To see this contrasts like a programmatic representation of a drill, like what I've shown here, with the analogous point cloud or mesh representation. The CAD representation, the program representation, is much easier to understand and extend than the mesh representation. But really the most celebrated property of programs is their universality or their Turing completeness. The fact that all computable functions can be expressed as some kind of program, and that means that in theory, at least in principle, they have the expressive power to capture the full range of problems that are solvable by intelligence. So if this is a fairly straightforward idea, if it has these appealing properties, then surely people have explored this before. And it turns out that in some sense, this is one of the oldest ideas within AI, and versions of it, or at least theoretical proposals, trace back to the late 50s workshop that founded the field. And with each wave of AI, this idea has been sort of reproposed in different versions. So for example, inductive logic programming and genetic programming are other versions of this old idea. And in spite of all these smart people having this very similar idea, it's never really taken off in AI in the same way that deep learning or graphical models have taken off. And there's a number of reasons why it hasn't really taken off, but the main reason is just that the space of all programs is vast, it's discrete, it's very hard to search this space. Combinatorial search is hard, and that poses challenges for learning. So in light of the fact that all these people worked on it and it didn't really quite pan out like how they hoped it would, why should we be returning to this idea again? Well, there's a few reasons. One is that we have better AI toolkits. And it's not just that we have deeper neural networks and more sophisticated graphical models. It's that, as I'll show in this talk, we have new ways of combining all of these ideas and bringing them to bear on this core challenge of combinatorial search. The second reason we should try again is because there are new techniques from the programming languages community for program synthesis. Now, typically these techniques were not developed with AI problems in mind, but a lot of their ideas we can repurpose and adapt for AI problems. And at that Dartmouth workshop, we were just getting out of the vacuum tube era, whereas now we live in the era of massively parallel compute. And one of the things that has accelerated machine learning over the past decade has been algorithms which can soak up these vast parallel compute resources. In this talk, I'll be introducing some new algorithms for program induction, which can effectively metabolize these new compute resources at our disposal, which I hope will allow them to scale in much the same way that other AI methods have scaled in the past few years. Another reason why we should be trying again is because we don't need to actually, like at that workshop, build a machine which is as smart as a person. We have lots of practical problems that we can work on. We have a kind of on-ramp of stepping stones. So problems like semantic parsing, or programming by examples, or computer-aided programming, which was pioneered by Armando, or inverse procedural modeling. Like all of these are different kinds of program induction, and they're all practical problems. And so if we advance program induction, we advance all of these other applications as well. So I'm going to structure this talk around 3 themes with the goal of showing how program induction can contribute to machine intelligence. So the first theme is going to be how program induction can contribute to high-level scene understanding, focusing on 2-dimensional hand drawings and 3-dimensional objects. The second theme is how synthesizing causal programs can be used to induce human understandable models, focusing on a case study in natural language. And the last theme, where I'll be spending most of my time, is on new algorithms for learning to synthesize programs. I'll be spending most of my time here because I see these algorithms as being part of how we're going to unlock the broad applicability of program induction by making machines which don't just induce one class of programs, but which can learn to specialize to many different domains. So I'm going to start out with visual perception. And I want to point out that vision is much more than knowing what is where. It's also about having a global understanding of scenes that cuts across the entire image. So for instance, here I've shown an image of an aqueduct, and I've covered up part of it, and I want you to imagine what lives in that covered up part. Can you mentally extrapolate this architectural design? So hold that in your mind, and then contrast that with what you see here. We can also use these abilities to impute missing objects. For example, here's an image that I lifted from a machine learning blog post, and they had cut out some parts of the image using ellipses. Can you infer what should go in those ellipses? Can you imagine a much bigger version of this figure? And if we can make machines which can do this, it wouldn't just do demos like the ones I just showed you here, it would actually be practically useful. We could use this to assist computer-aided design of mechanical parts or graphic design of visual patterns. So in collaboration with Dan Ritchie, who is at Brown right now, we have built a system which implements some of these ideas. And the way it works is by looking at a hand drawing, like the one I've shown on the left, and then synthesizing a high-level graphics program in a latex-like language, like that shown on the right. Now, just as you were able to mentally extrapolate that aqueduct, the system can also sort of extrapolate images by imagining bigger versions. So the way that works is by incrementing loop bounds. And if you do that, if you just say, like, what would it mean for the loop to be bigger, then you get an automatically generated extrapolation of the image. So look at the hand drawing on the left and ask yourself, what would it mean to make it bigger? And then contrast that with the machine output on the right. And we can do this for a range of images. So for each image on the top, ask yourself, what would it mean to just kind of make its patterns bigger? And then contrast that with the image on the bottom. So the way that this system works is as follows. We imagine that we see some image, and we want to infer a latent program, meaning a program that we don't get to see. Now that program, as an intermediate step, issues a sequence of drawing commands, which we also don't get to see. So we have a kind of 2-stage generative model where programs make drawing commands and drawing commands make pixels. That motivates a 2-phase inference pipeline, and that's exactly what we do. So in the first phase, a neural network acts as a proposal distribution for a sequential Monte Carlo sampler, a kind of stochastic search. And that gives us a high-level parse or a set of drawing commands. And then given those drawing commands, we use constraint-based program synthesis to infer a high-level program consistent with those commands. The issue here is that these constraint-based techniques, like many techniques in program synthesis, scale in the worst case exponentially. And so we use learning to direct the search toward promising regions of the search space. Once we have this high-level program, we can extrapolate it, as I showed you earlier, but we can also correct errors, as I'll explain now. So here's an example input drawing, and if you just give it to the neural network and ask it to interpret this image, it actually produces this thing here, which, as you can see, made a mistake, kind of hallucinated a triangle. But if you were to imagine trying to describe the global structure of this image, like write a program that described this image, that program would be much less naturally structured and would be much longer using this neural network produced image, because it would not be able to pick up on this high-level pattern that cut across the entire scene. So if you introduce a bias toward programs that are more parsimonious or more naturally structured, then the interaction of that top-down inductive bias with the bottom-up perceptual module can correct mistakes like the ones here. So this is a kind of interaction between top-down and bottom-up influences on perception. And you can do that for more complicated images like the one shown here. So we did this for two-dimensional drawings. They're very simple drawings. You might be thinking, can we do this for three-dimensional objects? And you can do a version of this for 3D. So I did this work in collaboration with Max and Evan and Felix. And what we did is we built a system which can look at a input 3D voxel field and then infer a program in constructive solid geometry. And then you can, for example, re-render that program or make the car do wheelies. The issue here is that just by going up an extra dimension, the search space actually gets much broader. So in particular, there's approximately 1.3 million different lines of code you can write in this graphics language. And to make complicated objects, you sometimes need to chain together 20 lines of code. This gives a total search space which is much larger than the number of atoms in the universe. So how are we going to tame this combinatorial explosion? So what me and Evan and Max and Felix did is we engineered a new algorithm which learns to search for graphics programs. And the way it works is kind of inspired by two ideas. One is that you want to execute the program as you write it. You want to draw the program or you want the program to draw what the code is doing in an online fashion, but also you want to learn to guide the search with neural networks and wrap that all up in an explicit symbolic tree search. So as an example of this in action, imagine we had this chair-like object to explain. We started with the empty program written as the empty set. So a neural network that we call a policy looks at the input image and then proposes some lines of code which get rendered. So here are three different examples from the policy. And as you can see, the cylinder on the top is kind of not at the right angle. The cuboid in the middle is too thick, and only at the bottom do we see a sample which looks like the base of the chair. So another neural network called the value function steps in and upweights parts of the search space which look more promising and downweights those that look like they're on the wrong track. And we alternate this policy and value function, and this allows us to scale to these longer, more complex programs. So we can do this for a range of shapes like the ones shown here. But what I think is more interesting is that the same kind of idea can also be applied for synthesizing a very different class of programs, in particular programs which edit text. And Evan and Max really took the lead on these text editing programs. And what they found is that this technique can be used to really strongly outperform the state-of-the-art in neural program synthesis for text editing. So there's a few things you should take away from this. One is that the inductive bias from having a programming language, like having loops and variables, gives you strong generalization properties. You can extrapolate rather than interpolate. The second thing you should take from this is that I don't think we should be too religious about what kind of AI techniques we use. We really should be pulling the best ideas from different traditions. We can use neural nets both for perception, but also for pattern recognition, for guiding combinatorial searches. We can use symbolic programs for inductive reasoning, and Bayesian methods are a kind of glue or a kind of universal units for building systems which can handle uncertainty at all these different levels. So now I'm going to talk about program induction and discovering models. And there's been a lot of work on automatically discovering things that look like scientific models from experimental data. So you might know this work on the top about discovering physical laws, or the work on the bottom about inferring gene interaction networks. And in cases such as these, they often explicitly cast what they're doing as a kind of program induction. Now, it is the case that one thing scientists do is they look at individual data sets and they say, what kind of equation or model would explain this data set? But scientists also do something else, which is they pop up a level and they say, I have lots of different data sets. What kind of universal principles or what kind of meta model, or sometimes we call them theories, would capture the regularities that we can find in all of these different data sets? So science really operates at multiple levels, and I think we want to study machine science at both of these levels. Now, I actually think that natural language, or the science of natural language, linguistics, is an ideal domain in which to study science at these two levels of action. So there's a few different reasons why I think we should be looking to natural language. One is that linguists very explicitly work at both levels of science. They work both on understanding individual data sets, but also on understanding the universal principles or universal grammar that cuts across all the world's different languages. Another reason is that there's tons of different languages, and this gives us a really rich and varied test bed that we can use to benchmark different algorithms. And this problem in theory should be tractable because both kids and linguists can pick up on these language patterns from a relatively small amount of data. So if we've got the right inductive biases, we should actually be able to make a machine which can discover language patterns. So then we're talking about joint work that was done with Tim O'Donnell, who's at McGill. So to give you a flavor of what I mean when I talk about learning language patterns, here's some data from Mandarin. The word for slow in one inflection is man, in another inflection is manmanda. The word for small is xiao in one inflection, in another inflection is xiao xiaoda. And if I tell you that the word for fast is kwai, I think that all of you are muted, so you can't actually yell out what you think it should be, but you're probably thinking that in the other inflection it should be kwai kwaida. And if you were a linguist, you could summarize this by saying, well, what's going on is you take the stem, you glue it onto itself. Here's some data from server creation. So the masculine form of the word for rich is bogat, the feminine form is bogata. Mild is blag in masculine, and feminine is blaga. If I tell you that green in masculine is zelen, what do you think the feminine of zelen should be? So most people can probably say, oh yes, it's zelena. And now I can mix things up a bit and give you the feminine form. So if I tell you the feminine form of clear is yasna, think to yourself, what is the masculine form? So you probably thought it was yasin, and you're almost right. It's actually yasan. And the reason is because server creation has a process called a penthesis, which inserts an ah in between two consonants at the end of a word. And if you're a linguist, you would describe that as insert an ah between two consonants at the end of a word. So using that program at the bottom. So there's entire textbooks which are chock full of these inductive reasoning problems. And we've built an algorithm which can solve most of the problems in these textbooks. So I showed you some of the simplest problems, and I'm going to show you one of the hardest ones and walk you through what the system does. You can get a sense of what the limits are. So here's about 100 odd words from a language that's related to Turkish. And I'm going to zoom in on a few words just in singular and plural form. So the word for bed is oron, and plural is oronor. The word for mare is ba, and plural is ba-ler. The word for cabin is iskap, and plural is iskap-tar. So I've highlighted the suffix in each case, and I want you to look at this data, and you should find this data really weird. It should be really puzzling, because in every single case, the suffix is different. So what's going on here? So if you give this to our algorithm, what it does is it says, well, the singular form is just the stem, and the plural form is just the stem plus lar. And this should also seem really weird because lar is not any of these suffixes. So what's actually going on is there's this ordered set of 6 rules that can be used to derive this data. And the way that the system came up with these 6 rules is through a combination of constraint-based program synthesis, like what you see in Armando's sketch system, also combined with some ideas from test-driven synthesis. So these rules, if you're not a linguist, might look a little bit cryptic, but all of them can be translated into English. And they all have to do with like moving around where the tongue is in the mouth while you say different vowels and things like that. So just to animate how this works, it also infers that there's some stems for each of these. And if it wants to explain some like a pronunciation of some word, like the word for beds, it takes the stem for bed, which is aron, concatenates it with the plural suffix, which is lar, to get oron lar. And then each of these rules is like a function which transforms that sequence and produces another sequence of sounds. So this was rule 1 operating, and then rule 2 didn't apply, and then rule 3 operates, and eventually you get this final pronunciation, which looks very different from its underlying or its original form. So the stuff in orange is what the system sees, and then the black stuff in the middle is like an execution trace or a derivation that it's using to explain the data. So we can do this for a range of languages. Here I'm showing the names of 58 languages from 70 different problems. And for each of them, we can compare different approaches. And we can measure how well different approaches do by comparing them with ground truth solutions that Tim and I annotated for each of these problems. So on the x-axis, I'm showing agreement, percent agreement with these ground truth annotations. And in different colors, I'm showing different approaches. So the dark colors are different versions of our system, and the yellow one is a grammar induction algorithm that was proposed last year. And there's a couple things you should take from this. One is that these colors actually seem to matter. Like, not all systems do equally well. In particular, what we're calling the full model does much better than these various ablations of our system. And the main variable that is different across these different ablations is a kind of inductive bias or universal grammar that's given to the system. So clearly this inductive bias matters. But you might be thinking, could we learn this inductive bias? And the answer is kind of. You have to build in some basics of representation. But once you build that in, you can then sort of embellish it or enrich this built-in universal grammar. So the way that works is you start out with data from some different languages, and then you say each of those data sets are explained by a different grammar, and then you unite those grammars by saying there's some universal grammar that can explain all of them, and then you just kind of guess or start out with some very flat and uniform distribution over grammars. So you imagine that you already know universal grammar, and then you infer grammar for each data set, and then you pop back up and infer this higher level grammar, and so on, and eventually you converge and you have some estimate of what each language specific grammar is and also what the higher level knowledge is. And doing science at both levels, of both individual grammars and also of this like universal grammar, proves critical for solving like the very hardest problems in the textbook. So for example, in that language that's related to Turkish I showed you earlier, you don't actually solve that problem unless you do inference at both levels. So this higher level knowledge really matters, and you can learn some of it. And interestingly, you don't really need millions of examples to learn it. So here we trained on 30 languages, and then the universal distribution over grammars that we learned generalized to the remaining 40. So in both this system and the system I talked about earlier, learning played a role, but it's still fair to say this was like a specialized system for certain kinds of linguistic problems and a specialized system for certain kinds of hand drawings. These were not like general program learning systems. So can we take a step back and say, like, what would it mean to make a system which could like learn to learn programs? So that's what we're going to talk about now. And I'm going to be talking about systems which learn to write code. And this is joint work with a number of people, but primarily Kathy, Max, Matthias, and Lucas. And you can think of this as being, we want to learn some domain-specific knowledge or some expertise that we need in order to do, in order to solve some class of problems or induce some class of programs. And I'm going to think of expertise as coming in two different flavors. The first element of expertise is going to be, what are the explicit concepts? Like, what is the language that you use to express solutions to problems in this domain? The second element of expertise is more like procedural knowledge or skill. It's how do I use that language to solve new problems? In engineering terms, that first element of expertise, the declarative knowledge, is really a domain-specific language. It's a language for writing programs. And that second element of expertise is really a domain-specific search algorithm or a synthesis algorithm. So to make things concrete, imagine we needed to write programs that are very simple. They just explain points on a curve, like this cubic function here. So in order to look at this curve that you see here and infer a cubic function, you need to both know explicitly about the concept of a cubic function. You need that word, you need that concept in your mind. but also you need to be able to look at a graph and say, oh, well, if it kind of goes like this, then it must be a cubic function. So there's two things here. One is you needed the concept, and you need to know how to recognize that that concept applied. So I'm now going to illustrate this idea of learning a library of concepts. I'm going to illustrate it in a classic program synthesis domain. So imagine we needed to write programs which sort numbers. We might get some input outputs like the ones shown on the right. And we might initialize some system with some very basic programming primitives like conditionals and cons and map and fold and things like that. So how are we going to get all the way from the left to a program that solves a problem on the right? So that seems like a pretty big gap because these primitives are very primitive. So what this algorithm does, it doesn't just solve this problem in isolation, it solves many different problems, and it tries to grow out a library of reusable functions, which are useful for solving many different problems. So if you look into its learned library, what you see is that one of the first things that it builds is this function called filter. And it builds that out of the earlier primitives that the system had. And filter, you can imagine, would be useful for sorting lists of numbers, but it's still not quite all the way to a sorting algorithm. So it's building this library hierarchically. And if you look deeper into this hierarchy, you see, for example, here, the 13th concept that it added to its library is this function which computes the maximum element of a list. So that seems much more like sorting, like we're getting much closer. And if you look into the final layer of this learned network of functions, what you see is a function which extracts the nth largest element of a list. And now we're almost all the way to sorting. And once we have concept 15, we can now write a very simple program for sorting lists of numbers. So here's a code it writes to sort lists of numbers. It just says call concept 15, meaning get the nth largest element as n is 1, 2, or 3. So get the smallest element, get the second smallest element, and so on. Now, this program is very short, and it's also very human understandable. But in principle, you could write a much longer program, which also sorted lists of numbers. You would just have to write it in terms of the initial primitives instead of the learned library of concepts. So if you were to rewrite this program using the initial primitives, it looks like this, which is much, much longer, and on the surface has nothing to do with sorting. It's also not just inscrutable, but also in an important sense, it's inaccessible. Like the program that it finds for sorting lists of numbers, it does in under 10 minutes. But if you were to try and do brute force search to try and find this long program, it would take on the order of 10 to the 73 power years, which is much longer than the age of the universe. So now I'm going to explain the algorithm which learned this library and wrote this program. And this algorithm is called Dreamcoder. And the reason why it has this name is because it's a kind of wake-sleep algorithm. It's related to the Helmholtz machine or wake-sleep neural network training algorithms. So the way it works is it iterates through what we call a wake phase, where it solves problems by writing programs, and a pair of interleaved sleep phases. The first sleep phase, which we call abstraction sleep, is going to grow out that library, that network of functions. And the second sleep phase, which we call dream sleep, is going to train a neural network called a recognition model to learn how to use that library to solve problems during waking. And we're going to apply Dreamcoder to a range of domains, some of which are, or all of which are shown here. So at a high level, from a Bayesian point of view, what you can think of this as being very similar to the universal grammar setup, where at the highest level, there's some principles that are universal across many different problems. Here, that's the library, and then that is used to write programs, which then solve some tasks or some problems. And you can see versions of this approach in prior work. So for example, this work by A.L. Dechter is, I think, one of the best examples of this idea. There's a few twists we're going to add here. One is that we're going to train a neural network called a recognition model to map from tasks to programs. And it's going to help address this challenge of combinatorial search. And we're also going to lean on some good ideas from the programming languages community. But from a kind of Bayes-eye view, this is the main difference, this neural network. So if you look at this picture, there's really three things we don't know. We don't know the library, we don't know the programs, and we also don't know the neural network. Because we have three things we don't know, that motivates a three-phase learning algorithm. And we've called those phases wake, abstraction sleep, and dream sleep. So during waking, we take our current library and we take a task, such as a problem specified by input-output examples, and we have the neural network look at the task and then bias a search over programs that are built out of components from the current library. And we search until we either solve the task or we run out of time. During the dream phase of sleep, we train the neural network to predict a distribution over programs, and it's trained on two sources of data. One source is just, we can take programs that we found during waking and we can train on those programs. But a more interesting source is programs that we fantasize or sample from the learned library. So we can generate an endless stream of data by generating random programs, running them to see what they do, and then calling that a sort of hallucinated task to solve. During the abstraction phase of sleep, we grow out our library by refactoring programs found during waking. So this step here really leans critically on some cool ideas from the programming languages community. So I wanted to walk through this step in detail to explain how it actually works. So how do we grow out that library of, how do we grow out that network of functions? So imagine that we had a program like 5 + 5. It's not a very exciting program, but it's a good example. We can write it like this in Lisp, and we can write it like this as a syntax tree. Now, if you look at just the syntax tree, let's ask ourselves, how can we rewrite this? So one way of rewriting it or refactoring it is to define a new function called 5 + x, and then set x equal to 5. And that's what I've diagrammed with the tree over to the right. We can also define a function which is x + 5 and x equal to 5, or x + x, or even 5 + 5 with x equal to 5. So all of these are semantically equivalent to the original expression, a relationship which I'm going to notate with this dashed orange line. And if you look at all these refactorings, they look almost exactly the same. They just vary in whether the leaf is a 5 or an x. And we can collapse together all of these refactorings using another idea from the programming languages community, that of using version spaces to represent large sets of programs. So here, the version space idea is this node I've labeled any, which means a non-deterministic choice. So you can choose any of the children of an any node and still respect these semantic equivalence relationships. There's lots of other ways we could refactor this program. We could abstract out the plus instead of the 5. We could even refactor the number 5. And critically, the reason why we're going to all this work is because this data structure is actually representing an exponentially large set of possible refactorings. So in particular, for each of these any nodes, we have two choices. And if you percolate those choices up the syntax trees, what you get is a kind of exponential growth in the number of refactorings expressed through this repeated doubling. So how is this data structure useful for discovering new library routines? So imagine that we have two programs, 5 + 5 and 4 + 4. So I've diagrammed a subset of the data structure in each of these cases, and I want to zoom in on two pieces of them that I've labeled A and B. And A and B look almost exactly the same. Now, A and B are really encoding sets of possible programs. And if you look at the intersection of those sets, there's only one member of that set, and it has this syntax tree, which I could write in Lisp like this, or if I were to give it a name, I would just call it double, because all it does is it doubles numbers. So what this slide is showing is, if you start out with 5 + 5 and 4 + 4, you can then learn an abstraction called double, which computes x + x. And you can imagine that if we had many such expressions like 5 + 5 and 4 + 4 and 3 + 3, then it would kind of pay off to learn this new doubling routine and add it to your library of concepts. So this seems like a lot of work to learn how to double numbers. And the purpose of this algorithm is not just to learn how to double things. So now I'm going to show a slightly more compelling case of this refactoring procedure. So imagine we had two problems to solve. On the right, I've shown a problem which is given a list of numbers, subtract 1 from each element. And on the left, I've shown a problem which is given a list of numbers, double each element. Now, if you have a function called map, which can apply the same function to a list of numbers, then solving these problems is very easy. You can just say map some procedure across the whole list. But if you don't, then expressing solutions to these problems is very challenging. So I've expressed here solutions which the system finds during waking for each of these problems, and they're very long and very cryptic looking. So now during the abstraction phase of sleep, what it does is it constructs these refactoring data structures. And I've shown here exactly one program in each case, which is represented by that data structure. And I've highlighted in orange a component that these two programs have in common. So now if we abstract out this orange bit here and add it to our library, then all of a sudden these programs get way shorter and also a lot easier to understand. Like one of them just says map -1 across the list, and the other just says map add something to itself across the list. And the motivation for this is that this is a way of jointly compressing all of the programs. So the number of refactorings grows exponentially, and there are about 10 to the 14 refactorings, but using this data structure, it can be represented on the order of about 10 to the 6 nodes and can be done in a few minutes on a laptop. So now I'm going to illustrate what this algorithm does in a few different case studies, focusing on graphics, planning, recursive programming, and physics equations. So for graphics, what we did is we gave the system a corpus of geometric designs like those shown here and told it to learn to draw these pictures. And I've shown here the network of functions that it learns when it's drawing these pictures. So here I popped out one of the pictures it had to draw, and below it the program it wrote to draw it. So you can see it's calling function 8 and function 4. And function 4 is a parametric routine for drawing spirals, which it learned and then added to its library. And function 8 is a procedure which repeatedly draws and rotates something. So function 8 is really a higher order function corresponding to the concept of radial symmetry. And if you look throughout the library, you'll see other routines like things for drawing circles or parametric families of arcs. So this library really represents the model's kind of explicit declarative knowledge. It's human understandable, it's expressed in code, but it's also learning some kind of implicit procedural skill in a neural network. And that skill is much more opaque and harder to interpret and understand. But what we can do is we can look at the training data for that neural network, the dreams. So dreams, remember, are randomly generated programs written from the learned library. So at the initial point of learning, here are what dreams look like. Most of them are relatively simple and unstructured. These are actually cherry-picked from 100 different dreams, trying to find the most interesting ones because most of them are just single line segments. So I've color-coded these not just to make them look dreamier, but also to show how it drew them. So it started drawing dark and then ended drawing light. So now we should look at dreams after learning. And what you see is a kind of like creative remixing or recomposing of latent concepts that it learned from the training data. So you can imagine that if you were trying to train a neural network to draw pictures, this is much richer training data than this. You clearly want to train on the dreams after learning. So we can also train it to use the same sort of idea to not draw pictures, but to build towers out of toy blocks in a simulated world. And if you ask it to do that, what it learns, instead of learning parametric drawing procedures, it learns kind of like parametric options for learning how to build these block structures. We can look at the dreams before learning, and we can also look at the dreams after learning. And once again, what you see is a kind of recomposition of concepts that it gleaned from the training data. So it's also illustrative to look at the system's learning trajectory over wake-sleep cycles. So at the initial point of learning, on the x-axis at 0, almost none of the problems can be solved. But what you see is a kind of bootstrapping action where over successive wake-sleep cycles, the problems it solves accelerate later learning. Now you might be thinking, do we need both sleep cycles? It seems kind of complicated. But if you ablate either of the sleep cycles, what you get is much lower asymptotic performance. We can also compare with a range of baselines. So for example, you might be thinking, do we really need this complicated refactoring algorithm? Like, could we just memorize programs wholesale? And it turns out if you memorize them, it doesn't work as well. You can compare with the state-of-the-art in neural program synthesis, a robust flow model, or I think a very critical baseline is this enumeration baseline, which just does a bunch of brute force search without any learning. And if you look across many different domains, you get the same kind of global picture, that you really do need both of these sleep cycles, and that learning unfolds over usually 5 to 10 wake sleep cycles. Roger, should I sort of wrap up really fast? We're trying to end it too.
No. It's I mean the thesis defense is, you know, there's a chunk of time, and so it's okay.
Okay. So this data suggests that maybe there's some kind of synergy between each of these sleep phases, and I think that there actually is some kind of synergy here. And the synergy works as follows. So we have three things going on. There's problem solving during waking, library learning during abstraction sleep, and the recognition model training during dream sleep. So as we solve more problems, we get a better library, like our network of concepts gets deeper and wider and has more domain specialization. But when you were looking at the dreams earlier, the dreams after learning were much more interesting, right? So as we get a better library, our dreams become richer, which then gives better training data for the neural network, for the recognition model. As the recognition model grows more attuned to the regions of the search space which contain promising solutions, we solve more problems. And so this creates a kind of positive feedback loop, where when one part of the system improves, it kind of echoes throughout the rest of the system. So this story is, I think, fairly intuitive, but there's also some empirical data to support it. And that empirical data comes from looking at the evolution of library structure over time. So if you look at the average library depth over time, what you see is that, shown in darker dots, libraries start out very shallow and don't solve very many problems. And then as learning progresses, they become deeper and solve more problems. Now, if you ablate the dreaming phase of sleep, two things happen. One is that the libraries get shallower, but also for a given library depth, we solve fewer problems. So this means that deeper libraries are correlated with better performance, and we get shallower libraries without dreaming. So dreaming bootstraps better libraries, but also for a fixed library structure, dreaming still adds something on top of that. The recognition model still helps. And analogous but weaker trends hold if you look at the total library size instead of the average library depth. So in the examples here, I was really looking, we were really not starting with a generic programming language. We were starting with some important domain-specific stuff. It wasn't like we just gave the system Python. So could we move towards something more like that? Particularly, could we learn something which looks a little bit less like a language and a little bit more, or a little bit less like a library and a little bit more like a language? So I'll look at two case studies. One that learns a language for physics, starting from a functional programming language. Another which learns that functional language starting from a very ancestral form of Lisp. So for physics, we took cheat sheets like this. I remember this from like AP Physics. And we converted 60 equations from these kinds of cheat sheets into symbolic regression problems by simulating random data. So then we asked the system to solve for programs that match that simulated data, but the twist is that we didn't tell it about vectors. Instead, we told it about lists. And if you look into its learned library and the first layers, what you see are these routines for manipulating vectors. Like it learns vector subtraction and vector addition and so on. And then as you go deeper into the network, what you see are things that look more like routines for physics, things like schemas for inverse square laws or for calculating periods. And this allows us to solve most of the problems on these physics cheat sheets. And if you look at the solutions that it finds, they're very human understandable. So for example, the solution to Coulomb's law just says it's an inverse square law with the difference of the two position vectors. But if you rewrite that into the initial set of primitives, it's no longer nearly as transparent. So here we started out with a functional language for manipulating lists, but you can also learn something like that starting from a more basic basis. So here what we did is we started out with just the Y Combinator and conditionals and a few other elementary pieces, and then gave it a problem set of around 20 different programming exercises. And if you look into its learned library, what you see in the first layer are these two routines called fold and unfold. And both of them are defined in terms of the Y Combinator. So they're both defined in terms of recursion. And what's interesting is that once it had fold and unfold, it then proceeded to never use recursion. So it built everything out in terms of folding and unfolding instead of calling out to the Y Combinator. So in the fold family, you have things like map and filter. In the unfold family, you have things like, if you know Python, the range function is a kind of unfold. And then there's also procedures which bring together the fold and unfold families, like indexing into a list. And once it had folding and unfolding, it sort of never used recursion ever again. And the fact that you can express everything in terms of folding and unfolding is, I think, a really cool fact. It's called sometimes origami programming because you're just folding and unfolding things. And I'm pointing it out here because it illustrates a broader point of this, which is that in this algorithm, you're not really stuck with the symbols you start with. Like here, we gave it the Y Combinator, but then it very quickly did a kind of change of basis and switched to using these fold and unfold routines. Now, one catch here is that we were starting from something that was very basic, and then we learned a whole bunch of high-level abstractions starting from relatively little training data. So this required a lot of compute. And often there's kind of a trade-off between how much compute you use and how much data you use for problems such as these. In particular, this experiment took close to a year of compute. But I didn't have to wait a year because this algorithm is able to scale to a large number of CPUs. So this experiment took around a week. So one thing you should take from this is that symbols aren't necessarily interpretable, but if you learn your symbolic language, then not only will it be better for solving problems, but it can also be more human understandable. The second thing you should take from this is that maybe you could learn from scratch, but you don't have to. Like with programs, you can build in what you know how to build in and then learn on top of that. So now I just want to take a few minutes to look forward. So to recap, what we have is a kind of toolkit for program induction. And it's trying to address this core challenge of combinatorial search. And the way it addresses it is through different kinds of learning algorithms, but also ideas from the programming languages community. There's many open directions. So here I've illustrated a few immediate directions. One is to combine these program induction ideas with semantic parsing. So this is something that Kathy Wong has really been taking the lead on. And if you think about it, like usually when humans are communicating what a program should do, they don't give input output examples. We use language. And most of what we know, or a lot of what we know as humans, we learn from language. And the work here has not really made contact with natural language semantics, but that can and should change in the immediate future. I've talked about how we can synthesize human understandable models for a particular domain of science, namely linguistics. But I think that the idea of doing science at multiple levels, both at individual data sets and also at the higher level, is something which can be more broadly applicable to other areas of science. Most of this thesis has been about what program synthesis can do for artificial intelligence, but these techniques for learning how to synthesize programs can also be used to kind of loop back around and help move program synthesis like even more out of the lab and into the real world. Program induction didn't really start as an engineering project. It started as a theoretical project back during the early 60s. And this early theoretical work is really inspiring, but it was also about solving a single hard problem in isolation, whereas what seems to work much better is jointly solving many interrelated problems. So I think that we need to revisit these basic theoretical issues, both to understand why and where our algorithms will work, and also to suggest ways that they can be improved. In this talk, I discussed some of our work with modeling physical objects or three-dimensional objects, but I think we can push this much further. We're modeling something like the physics of the world as a kind of like CAD engine representation. And I'm very excited to work more in this area, and I'll be spending my gap year with Max and Tejas, working for them, doing stuff on this modeling the physical world area. So these steps are in reach, and in many versions, we're actively pushing those lines. But taking a step back, like, what does this say about the future of machine intelligence? So I think there's a number of things we want in the future of machine learning. One is we want systems which can generalize really strongly, which extrapolate instead of interpolating, and which can do so without needing enormous amounts of data. At the same time, if we do have more data, we want systems which can bootstrap or learn to learn, and where that learning to learn is enabled by learned representations. One way of seeing library learning is that it's a kind of symbolic deep representation learning that has its internal representations built out of symbolic code. But I think what we want most is we want machines that don't only make predictions, but which also discover something that looks more like knowledge, something that humans and machines can understand and contribute to. Now, to be clear, I'm not saying that program induction is all you need in order to get all of this. I think we need lots and lots of good ideas if we want to have all of this in the future of machine learning. But I hope I've convinced you that program induction can be a core part of the story here, and that the steps we're taking are headed in directions like these. So that's it for the kind of technical part of the thesis defense, but I wanted to now talk about like the people. So I feel really lucky to have had these amazing advisors. Like as Josh said, I had the opportunity to start working in his lab, Kokosai, as an undergrad, and it was a fantastic experience and convinced me to, you know, like that experience convinced me I just like needed to stay here and keep on doing more stuff. And like I've really grown a lot by getting to be in that environment, and I'm incredibly grateful. I met Armando sort of right at the start of grad school because Zena told me that I had to meet him. And I'm really, really glad that that happened. Armando really helped me grow intellectually and made grad school more pleasant. I mean, both Josh and Armando did that, and it's like the lab environments at both ends is just great. So thank you guys so much. It's been really wonderful. Also, there's lots of super cool people that I got to work with, and this is only a subset of them. Evan wanted me to put the picture of him cutting my hair during quarantine. And so thank you for the haircut. But also I want to point out Eyal, who was the person who mentored me while I was an undergrad, while he was a grad student, and point out Clement and Lucas, who are undergrads that I got to work with while I was a grad student. Like I really like that about MIT and BCS, and how you know, we all get to work together, and it goes across different sort of academic generations. And it's been really wonderful to work with like this group of people and other people that, yeah. But also my family and friends have been incredibly supportive, and I'm really grateful. And I, you know, been at MIT for a decade, and you've been very patient. So thank you so much. Also the departments, the administrators are very helpful, especially with scheduling the defense. And if you're on Twitch, thanks for being on Twitch or on Zoom. So that's it. And I'll take questions.
All right, I'm going to unmute everybody, and so we're going to be able to do, just be ready to applaud. 1, 2, 3. Everybody's unmuted. So good, son.
Oh God, this is terrible.
All right, I'm now going to remute everybody, and we're going to move into the public Q&A part of the whole thing. Everybody is muted at this point, so go ahead and raise your hand and or put your question in the chat. Okay, great, Martin, you have already. I'm gonna call on Martin because he was fast to the chat. Here you go, Martin. I'm asking you to unmute yourself.
Hi, thanks. I had the question prepared. This was an amazing talk, by the way. I was gonna ask a few questions, but I think you've answered all of the rest like during the talk. So yeah, I wanted to ask, what do you think is missing right now to go from these problems to something like Dijkstra's algorithm, both in terms of the methods and in terms of the supervision? And for example, in terms of not just finding a correct algorithm, but finding one that has low complexity.
Yeah, so that's a fantastic question. And if you look at the sorting algorithm that I showed earlier, it's actually a cubic time sorting algorithm. Yeah, so one ingredient is you need a preference toward efficient programs. But I think that like one of the ways that human engineers make efficient programs is they first start with like a slow version, and then they start with that as a spec, and then they construct the optimized version. So you would need a different kind of system where the supervision is not like input outputs or natural language or an image. It's actually another program. So it's like going from one program to another. So there, I think like you probably want to combine like learning methods with something which can actually work with formal specifications effectively. So something like an SMP solver. Yeah, but if we want to make machines which actually like help us do software engineering, instead of just helping us like write LaTeX or something, then clearly like what you're saying is very critical.
All right, the next question is from is Cadbox. Cadbox, go ahead and unmute yourself and ask your question.
I cannot unmute.
Cadbox, are you there? Try it again. Okay, I think you're unmuted. Go ahead.
Oh, okay, amazing. So it seems like the dream coder is kind of like a simulation that you're running, right? You're dreaming and you're compressing, and it just keep going forward, and you give it a fixed set of initial input, which is kind of a curriculum of program, and just gets smarter and smarter over time. So is there like what do you feel about this whole setup? Because it's not receiving new information, right? From an information point of view, like all the information are there to begin with, and it just kind of evolve over time, and it just gets smarter, right? Like it's not getting additional bits. So is it kind of like a game of life thing where you could say, well, all the information is contained in the initial configuration, but it's still interesting as you evolve it? Like what's your, yeah, just like vaguely speaking, what do you feel about it?
So you're kind of injecting knowledge in a few places. One is the training set, like that's important. The other is the initial language that you give it. But in terms of going beyond that, like one important thing that the system doesn't do that people do is people make up their own problems. They say like, oh, like it would be just cool to like draw these kinds of pictures, for example. Like when kids are learning to draw, we don't give them 100 images and say, copy these images, right? Or I mean, maybe we do that with like coloring books sometimes, but mostly kids like will like creatively draw what they want to do or like build what they want with Legos. We don't give them like a training corpus of 100 tasks. So I think like a nice next step would be to make systems which can make their own problems up, either motivated by like curiosity or aesthetics, or also as a kind of stepping stone towards solving some hard problem. Like often as like researchers, especially in AI, like that's kind of what we're doing. Like we want to make machines which are smart like people, but that's impossible given the tools and ideas we have right now. So instead we make up these kind of like easier stepping stones. We say like, oh, it'd be like more attractable to work on like this specific region of intelligence.
All right, Eli is next in line. I'm asking you to unmute yourself, Eli. Go ahead.
Okay, and I'll be on video as well. Hi, Kevin. So I thought one of the most interesting results that you found was that when learning a language, the learning engine learned fold and unfold, and then you said did not use recursion after that. So in functional programming, we would call that learning, you know, an anamorphism and a catamorphism. And I'm actually wondering, did it acquire any explicit representation of what those are? Or would there be some way, do you think going forward, there's a way to build in inductive biases towards finding those kinds of sophisticated algorithmic schemes that let you describe a variety of algorithms and then just get rid of your primitive? Like forget about primitive recursion.
Right, yeah. So in terms of inductive bias, I think that there's sort of two answers. One is that, and I'm not really sure which answer is right. One answer is that fold and unfold are just kind of objectively mathematically better, and somehow you should be able to derive that. And maybe if you had a inductive bias which preferred a basis that had a small number of primitives which are complete and which are only used in very restricted ways, then that would naturally prefer fold and unfold over the Y Combinator. The second answer is that maybe there is no first principles basis for preferring anamorphism and catamorphism. And it just happens instead that empirically, the kinds of problems that humans care about are better expressed using these morphisms. So like if you crawled GitHub, I'm sure you'd see more instances of list comprehensions than you would of explicit recursion within Python programs. So yeah, I think it would be interesting to see if we could work out like an inductive bias, which just preferred this like either fold and unfold or like some other equivalent basis, or could discover like the full zoo of morphisms that people have. But I'm not totally convinced that's the case. I think it might just be the problems humans care about are better expressed that way.
Wonderful. Just as a comment, with exactly what we hope to see with outstanding thesis work and thesis talks, we are getting a slew of wonderful questions. I'm doing my best to keep track of the question order. Next up is Samuel Tenka, then Zena Tavares, and then I'll work out who's next after that. So Samuel, I'm asking you to unmute yourself.
Oh, cool. Yeah, thanks, Kevin, for the wonderful talk. I'm just wondering whether you could say a bit more about like what theoretical directions lie ahead. For example, you showed Kolmogorov's book, and wondering like, are there specific theoretical problems in extending Kolmogorov complexity to like understanding what it means to efficiently bootstrap across multiple tasks or something like that?
Yeah, I think that you kind of want to look at like resource-bounded Kolmogorov complexity. Like you want to say, if you have some problems that have high mutual algorithmic information, and also that the programs run quickly, then like they should be jointly solvable or something like that. And something like that feels intuitive. It might be a way of like sharpening up exactly when these algorithms are going to work. Like right now, the only intuition I have is like, well, if the problems are interrelated and there's some easy ones and some hard ones, then it should work better than if you only give it hard problems. But there should be some way of formalizing that and sort of, figuring out exactly when it should work.
Zena.
Cool, thanks. Thanks, Kevin. Great talk. 2 quick questions. One, how should I, like, as a Bayesian, how should I interpret the learning component? As in, the kind of the standard framework is I have some private programs and I do inference. But in your framework, I'm learning this library. So is there a straightforward Bayesian interpretation of this learning process, or should I think of it in different ways? And the second question is, do you have any thoughts on learning data structures? Because real programs have data structures, and also learning languages themselves.
Yeah, so those are great questions. So the library implements a prior, and the library has some weights, so it kind of isn't exactly a PCFG, but you can kind of think of it that way. Like the difference between it and a PCFG is like not very interesting or important. And in terms of learning data structures, that's something that I very badly want to do. Like I don't really see library learning as being learning a domain-specific language. Like a domain-specific language, like what human software engineers actually develop and use, includes like control flow and like evaluation strategies and data structures and so many other elements that I'm just taking for granted. And data structures and synthesizing types are like the next thing to do after you can synthesize functions. So it's what I think what we should be doing next, but I haven't done it. I'm not really sure how to synthesize new types or data structures.
Great. Next up is Ronald Alvarez. Ronald, go ahead and unmute yourself.
All right. So Kevin, one of the really fascinating aspects of this project, of your work, I believe is the dreaming mechanism of Dreamcoder. And so I'm wondering, first of all, how closely does this sleep-wake mechanism of Dreamcoder resemble what we know about human sleep? And also, do you have a sense for other ideas from biological sleep that we can take advantage of in the future to improve learning?
Yeah, so I could definitely, there's a way of drawing analogies to biological sleep. I'm not a sleep researcher or an expert, so I feel like if I draw those analogies, I'm gonna get it wrong. And there's always some danger in sort of anthropomorphizing AI systems too much. right? Because then you might think like, oh, it's like maybe the system would work better if it looked less like biological sleep, right? Because it's on silicon, not in neurons. But just to say what little I know about actual sleep does come in two phases. There's kind of the dreaming phase, which is associated with more like implicit procedural knowledge, and like a memory consolidation phase or a slow wave phase where you like form new abstractions. And roughly that is kind of what it looks like here. But this is not like a theory of sleep or a model of sleep, and maybe the way sleep works in the brain is not the way to make our systems. But what you're saying about looking closer at human sleep and maybe drawing inspiration from it, I think is a really good idea. Like there's kind of a balance between wanting to be biologically inspired because they have good ideas, but also, you don't want to say that an AI is good purely because it's biologically inspired. So like one thing about sleep is, dreaming tends to not really, it's not literally just forward samples from your generative model. It's often like taking waking experiences and then like remixing it. Like you saw something and then you might dream something that's more like it. Now I'm like really out of my depth. Like I don't want to say too much. I feel like I'll probably say something wrong about biological sleep. But I think that there probably are some good ideas there we can mine.
Great. Clement is next. I'm asking you to unmute yourself, Clement.
Thanks. Yeah, my question is about synthesis of synthesis algorithms. So it's a lot in the line of the two previous questions that were about data structures and Dijkstra's algorithm. Like, what do we need? Like, what sort of domains do you think are good for grounding synthesis of synthesis algorithms? And maybe on top of that, are there any directions that involve casting the implementation of the synthesizer of your system as a task for itself to solve?
I like that idea, like turning it on itself. You would kind of need like a data set of data sets. Here I'm just kind of quoting something that Luke Cubitt has told me about, that he has been thinking about for a while. So I would recommend like chatting with him also. But yeah, you would kind of need, like, if you wanted to really, like the way that, we came up with Dreamcoder is we thought abstractly about program synthesis and thought like, well, what would a good program synthesizer be? But we could only do that by drawing on a lot of practical experience building program synthesizers. So if you wanted to make a machine which synthesized a new synthesis algorithm, it might need like a data set of data sets or something like that.
Thanks.
Vikash Mansinga is up next. Vikash, I'm asking you to unmute yourself.
Hi, can you hear me?
Yeah.
Kevin, thank you. It's really lovely to see how far Dreamcoder is able to get. It's really beautiful. So thanks for the great work. I had two questions. The first one is, can you talk a little bit about how much energy is needed to do this kind of learning? And how should we be thinking about narrowing the energy gap between Dreamcoder and the minds? That's one question. And the other one, sort of a related question, it was really awesome to see the ablation study, to get a sense of the role that each phase of the Dreamcoder technique played in setting up positive feedback. That was really great to see. I found myself wondering, if I look back over the literature on program learning, including genetic programming, how should I be thinking about the way that classic genetic programming techniques, searching over the same structures of DSLs, libraries, programs, traces, and input-output examples, which they could do, how should I think about how those techniques might compare to Dreamcoder?
Right. Yeah, so those are great questions. The energy gap between the brain and the Dreamcoder experiments we ran is enormous. Like we were running these things on like 64 CPUs, sometimes 100 CPUs. So the number of watts we were burning was way more than you see in a human body. In terms of how to get that down, Dreamcoder is still doing a kind of blind search. Like it's biased by the neural network, but not in a very deep way. So if you remember the bit of the talk with the chair being built up incrementally, where like there was a policy that was like proposing bits of the chair and the value function was saying like, oh no, it doesn't belong in the chair, but that belongs in the chair. So we're not doing that in Dreamcoder. We're asking the neural network to just output a distribution over programs, and then we just enumerate from that distribution and check to see if anything in the distribution is correct. So doing some kind of smarter search, I think, would be the main way of getting Dreamcoder to consume less time and fewer watts. In terms of comparing with genetic programming, the main qualitative difference is that we're looking not at solving a single problem in isolation, but at solving many interrelated problems. And I actually think genetic programming or something like it might be synergistic with Dreamcoder because you could use it as a kind of interloop. Like it might be the case that instead of doing neurally guided enumerative search, which is what we're doing right now, we really should be doing something more like genetic programming that might be informed in some way by a learned pattern recognizer. So I see them as just kind of solving different kinds of problems, and it might be the case that really we should be importing more ideas from that community.
That's great. Next, I'm going to read a question. Jutian Yang has asked me to read the next question. The question is, in building the programs that achieve the tasks such as list manipulations, do you see multiple solutions that are found to the same problem? This can happen a lot when we move on to synthesizing programs that solve more complex problems, such as making an apple pie or generating a question.
Absolutely. Yeah, you do see that. So for example, the sorting algorithm that I showed was the one it converged to after like a dozen wake-sleep cycles, but it kind of bounced around a few different sorting algorithms. Like ultimately, the one it converges to tends to be the one which shares common structure with other problems. So for example, moving beyond like the list domain, when it was learning to draw those geometric designs, sometimes it'd be like some family of spirals, and a smaller member of that family could be easily drawn without seeing it as a spiral. And so early on in learning, it would express it using some low-level stroke moving routines, but then later in learning, it would recognize it as being an instance of this family of spirals.
Great. The next question is from Michael Chang. Michael, go ahead and unmute yourself.
Hi, Kevin. It's a very inspiring talk. Thank you so much. So my question is, one of the key properties of Dreamcoder is that it builds new concepts on top of what it already has learned. So it treats these previously learned concepts as immutable primitives when it learns something on top of it. But what if the previously learned primitives were learned incorrectly? And that would lead to suboptimal programs that you learned later down. So for example, one example could be something like the O of n cubed search algorithm. If it later builds a program that uses the O of n cubed search algorithm as a subroutine, it could be that it just realizes, okay, I already have a search algorithm, so there's no need for me to learn a more efficient one. So like, are there more efficient ways to deal with this problem of suboptimal primitives other than like just hoping that the learner resamples better primitive concepts to build upon?
Yeah, so the issue that you raise is a very real concern, and we do see it happening. So it might learn some abstraction which is not really optimal, and then it's just kind of stuck with it. We don't have any kind of forgetting mechanism, so it never really forgets something once it's learned it. I think we should have a forgetting mechanism. And when I was showing those learning curves earlier with the error bars, one of the reasons why you get those error bars, why there's variability across runs, is because of exactly the issue that you're raising, that it sometimes just learns the wrong concepts, and then it keeps those concepts around forever. So we need to address exactly what you're raising.
Great, and we have a question from Victor. Victor, let's see, sorry, I need to ask you to go ahead, you can unmute yourself.
Okay, I think I unmuted myself successfully. So my question was how easy it is to determine if something will start to produce results in the finite time, essentially, specifically induction. Is there any way to anticipate if it's going to eventually give you a useful induction, or do you just kind of have to watch training loss over time like you would with more conventional neural networks?
I think that for programs, it's a little easier to kind of guess if it's going to work ahead of time, because you can kind of imagine the code, but you also do get surprised a lot. And that's kind of one of the reasons why I think we should do this like theoretical work. Like maybe we'll get some kind of insight there. Like I'm not a theorist, so I'm not, it might be just like off base here, but like it is a little more like both in terms of predicting whether it's going to work and in terms of understanding what's learned. It's usually easier to figure it out than it would be with a neural network. You know, like I assume a lot of people have seen like GPT-2 and GPT-3 that have been out recently, and I was just totally blown away by that. Like I didn't think that would work as well as it did. Whereas I was sometimes surprised by what Dreamcoder did. Like it was kind of like 50-50. Sometimes it was like, oh yeah, I kind of knew it would do that, or like, okay, it's a little not quite how I thought it would turn out. It's kind of a mix.
Cool, thank you. Great talk.
Thanks.
All right. Okay, Giulio Ruffini has one more question. This is, by the way, we're going to need to close the public defense section too, so pretty soon. So this is like last call for questions. So if you have a question you want to ask, think of it very quickly because we're going to end very soon. But Giulio, I'll call on you. Go ahead and unmute yourself.
Hello. Thank you very much for the great talk. I really enjoyed this, and I think it's a great step forward for the Kolmogorov vision in machine learning. So the question I had is whether, when dealing with data with noise, have you thought about any way to integrate notions such as the structure function to decide when to stop adding bits or lines to the code in order to fit the data?
Oh, I have not at all. That's a really interesting idea. Like my opinion about noise is just like, well, you write down a noise model or you train like a perceptual loss function. Like the way I thought of it is just like a very standard, you know, I'm someone wearing a machine learning hat. That's how I think about noise and uncertainty. But you're totally right. Like that, all the literature on Kolmogorov complexity has its own twist on how to think about noise. So no, I hadn't thought of that, but that's a good thing to mull over.
Okay. Well, thanks again.
Great. Max Nye has a very quick question. Go ahead, Max.
Hey, Kevin, great talk. I'm wondering if you've thought about how we could take the idea of compression, which is obviously key, and apply it in scenarios where we're outside of the lambda calculus formalism that you've done for the Dreamcoder project.
Yeah, I think that at a high level, it's always just compression. Like maybe you have other sources of supervision like natural language, but at the end of the day, you're trying to decrease some kind of code length. You're trying to find like a parsimonious basis for expressing solutions to problems. So you should be able to just import that idea to inductive logic programming or like different kinds of logic or whatever. And people have done things like similar to like the Dreamcoder compression and other areas. So I think you can just kind of do that as long as you come up with the analogy of refactoring for this other representation. One issue though is that maybe compression isn't, maybe the most compressive representation is not the best representation for search. Like maybe there's some abstractions which are very compressive but are really hard to reason about. Like it's hard to tell when they're the right tool for the job. And so there might be a trade-off between the most compressive representation and the representation which is best for search or best for interpretability or something like that. Like these hylomorphisms and catamorphisms and stuff like fold and unfold. Like, I don't know about you, but I never use unfold. It's a really weird thing. It is technically a very parsimonious way of expressing lots of programs, but I find it very hard to reason about. Like most programmers find fold supernatural, or at least not too crazy. Most people have never heard of unfold, even though it's a very compressive way of expressing many kinds of recursion patterns. So maybe it's not just compression, but also like what's easiest for humans and machines to reason about.
And one more very quick question from Clement. Go ahead.
Hi. Again, thank you for the great talk. What do you think is a way to build the communities of people that work on program synthesis and program induction?
I think exciting applications are the right way to build the community. Like that's how you generate enthusiasm, I think. So yeah, I mean, GPT-2 is really on my mind because or GPT-3 because it was just released. Like people are so excited about it because it does all these cool, amazing things. People were less excited about like neural networks when they weren't doing these cool, amazing things. So I think that the way to build the community is to like make the demo, which is the AlphaGo moment for program induction.
Thanks.
What a perfect final question for a really stellar defense. I think I'm going to unmute everybody once again, and we're going to give Kevin one more round of applause. The unmute is off. I'm unmuting now. Sorry, we're going to have to. Yeah, we're going to have to end. Congratulations, everyone. Congratulations, Kevin. Very good.
Yeah, super swole.
Yeah. Okay. Sorry. All right, you're all muted again. Wait, so what's going to happen is, we're going to end the public session in a moment, but before we do that, Josh is going to he's going to post a link to a post-defense celebration, and it's coming in now. So make sure you note it down, take a moment, copy and paste, because when you leave, you won't be able to get back in. All right, so at this point, you're all doing that. I'm gonna create a breakout room, and the committee are going to go inside it, and everybody else is going to be left behind. So there's not going to be much for you to do, but you know, we'll see you in the post defense setting. So thanks everybody, and I'm just going to sort of create this room as we're.
All right, chat, we're done. Thanks for viewing Thesis Defense. It has been great. I will see you in the next installment. Goodbye.